release the first question on that next worksheet. That was in the method of initial problem, and you should have been able to do all but maybe 2 or 3 of them. We'll see. We'll get there. Should be done tonight. I'll shut up here. 2.5 more minutes or something.
That's what I was thinking too. Yep. What else? Some of them.
Or I do, right? As long as there's a pictures and markers on the butts, you know that. Oh, yeah, that's what it's I looked over. What if you do and I don't know? Alright, just notice our.
I'm in for a demonstration in about a minute. Right in the middle of
Remember, I don't get,
You're good at doing it.
all right, questions, anybody? Whines, moans, fetches, complaints, yes, ma'am.
We left off last time with the rate relationships for the first order, right? That's where we stopped?
Yep.
So we're gonna go to the second order today?
We're not gonna do that much on second order, but we got a few more things to finish up with that,
Okay,
okay?
because we didn't go over like that part of the.
No, I'm just giving it to you as a chart.
Okay, all right,
So,
make sure.
because some people need to have everything in front of them, so I figured I'd just leave that up. That way, in case you need it. You should know for second order, the rate law, the units, and how to recognize it. I don't think we'll have time to do too much with second order reactions for, time. Okay? Anything else? Anything else making you crazy? Labs, yes, we know about labs, but your lab from last week, if you got data at all, I don't know how you did, you should have been able to get a line, and from that line, you should be able to get a slope, and your slope is the rate for that particular reaction. You did 4 runs, so you have 4 rates, and for each of them, in general, for your lab last week, the rate, which is your slope, would be equal to a constant times the peroxide to the sum power and the iodide to the something else power. And it was set up so that you would divide all of rate 2 by all of rate 1 in order to find the order with respect to peroxide, and then all of rate 3 by all of rate 1 to find the order with respect to iodide. That's how it was set up, and that's how it was supposed to go. And it was supposed to be peachy keen, and you were supposed to have nice numbers. And if you don't have nice numbers, you should at least have numbers. And I will grade your lab based on how true you are to the information that you got. Okay? I'm not going to say that everybody has to have this order for this, or this particular value for the constant. But you should be able to calculate the concentrations without any difficulty. This is just dilution, M1V1 is equal to M2V2. Peroxide, you have to find out how many moles you got first by using the density formula. And then once you get that, then you find the molarity by taking moles divided by the 0.05 liters, 50 mils, which is everything it was. And then after that, piece of cake. Okay? Honest to God, piece of cake. It's method of initial rates, and we did about 84 of them last time. But if you need to see something, let me know, or if you need to go over the problem from the worksheet, which I'm sure everybody did already, and I can do that. If you notice among the papers that were up here, you have the review topic for exam number 2, and the first thing is kinetics. There will be another one on molecular equilibrium. I figured I'd give you this early, so you can figure out what it is that you don't know, from what, based on what you should know versus what you don't know. So you can start to panic early, than you did last time. Last time you panicked 15 minutes before the test. This time I want you to start a little bit earlier than that, all right? Try problems.
What date is the?
Don't know yet, because we haven't even looked at molecular equilibrium yet, okay? But it'll go relatively fast. But that's how I think of all of them. I don't know how fast it really will go. All right, last chance, questions? Problems? Okay, cool. All right, you guys didn't respond, so I get to go ahead. Go ahead, question? All right. I don't want to step on your moment. All right, last time we looked at the relationship between concentration and time. The previous information with method of initial rates was concentration related to the rate of the reaction. Then we looked last time at concentration versus time, and took a look at two types of reactions first. A zero order reaction, where things occur at a steady state, and note the characteristics. Some nasty teacher, for example, on your next test, might give you a couple of graphs and say, which of these is the graph of the zero order reaction? The way you know is by the units. If it's concentration versus time and you get a straight line, then you know automatically it's a zero order reaction. But because these things occur at a steady state, what you have now is going to depend on what you started with minus the constant times the time. The constant is how much is disappearing per unit of time. So constant, how much is disappearing per unit of time from what you started with, will give you what you have now. That's a pretty straightforward relationship. It's the first of the actual formulas that you should probably remember. But it's not difficult to do. You could be asked to solve for the concentration now, or you could be asked to solve for time. And we did an example of each one of those. So anybody have any questions, problems with that? That was okay. Then we moved on. Notice I just kept going, step on a moment. Then we looked at the relationship with first order reactions. And with first order, you got a little bit of a problem because the rate is going to be changing as the concentration diminishes. As more and more of the reactant is used up, the reaction has a tendency to slow down a little bit. And it's difficult, therefore, to give you an exact relationship for a gross change in concentration with time. We have to look at a way of straightening out that line. And the way that you can do that is to take the log of the concentration versus time. First order reactions give you a linear relationship with log of concentration versus time. And the reason being that we have to actually find a way to relate these, relate the concentration versus time. And since we're dealing with minute changes in concentration with time, we wound up taking the derivative minute change in concentration with tiny increments of time change. And then once we have that statement, we know that the rate law for a first order reaction is the constant times the concentration to the first power. Equated those and then took an integral and found out that yes, indeed, it is logarithmic. That's how we can get this relationship. And for those of you who didn't like any of that, I said don't even look at it, because this is a bottom line version of it. The log of the concentration initially versus what it is now is equal to kT over 2.3. Or you could simply say, if you wanted to keep it natural log, the log of A0 over A is equal to KT. The 2.3 is just thrown in because we're using base 10 logs. But the reason I do that is because it's easier to see sometimes what the value should be. Now, there were a couple of types of problems that you had to be able to do. One is where you don't know or want to find the concentration at a later time. In that case, you have log of an unknown thing. So you do the side of the equation that has all of the numbers, get a value, and then we wound up with log of something over unknown is equal to number, and had to take the anti-log of both sides. Taking the anti-log of this side cancels out the word log. Taking the anti-log of this gives me a value, and I'm left with concentration for the current time. Most people are okay with that, or at least you nodded sagely when I said, are you okay with that? And you said, uh-huh. So I just took you guys at your word. The other kind of thing that you might have to do would be to find the time. If you had to solve for time, you would have both values on this side of the equation. So you just would divide and take the log and then solve for the time. It's a little bit easier, but make sure you know what the math is and make sure you know where the magic buttons are on your calculator for this. Get comfortable with your box. It will be your friend. Okay, any questions about that? You're okay. Cool. Now, the other thing that we took a look at is, well, how can you do these things if you need to scale up or scale down? Sometimes you don't know the initial concentration, but you can express it as a proportion, as a percentage of what you had initially. So there were some problems, for example, where if you needed to know how long it would take for 65% of the substance to react. Okay, so suppose you have a reaction where you've got stupid magnet in the way. We have the constant is equal to 2 times 10 to the negative 4 per second. So we know it's a first order reaction. And I want to know how long for 65% of a sample to react. Piece of cake. Because what you need to do is simply to state this relationship mathematically. If 65% has reacted, then what you have now is 35%. So if I have A0, this is the initial, and A would be what I have now. So if this is A0, then this is 0.35 times A0. 65% is gone, 35% remains. So what I have now is 0.35 times what I had initially. So now I can just plug it in as if this were a real number. I can take log of A0 over 0.35 A0 is equal to 2 times 10 to the negative 4 per second times the time. And by the way, if the time is given to you in minutes or hours or years, it doesn't matter. You do not have to change the units to seconds all of the time. Whatever units they give you for time, keep those same units. And over 2.3 to keep it kosher. So, magic box time. I've got A0 over A, so I wind up with the log of 1 over 0.35. 1 divided by 0.35. Get the log is 0.46 about. And on this side I have 2 times 10 to the negative 4 divided by 2.3. So I have 8.7 times 10 to the negative 5 times T. Simple problem. Look for this kind of thing on your final. I mean, as long as you know the formula, the problem is pretty straightforward. So that times 0.46 gives me a time of 52.90 seconds. So you definitely have time to go out for coffee while you're waiting for this thing to run. Okay? Questions? This would work no matter whether you started with 1 molar or started with a huge tank of this stuff at the refinery. Because of the way this reaction proceeds, this first order, we can just plug in and go for it. Questions? Problems? Okay. You use the same kind of thing to figure out a relationship for a half-life. For a half-life, the amount of time that it takes for 1/2 of the sample to decompose, my writing's getting too flamboyant, sorry. T1/2, this is not a number there, that's just a designation. The half-life is a designation. The amount of time it takes for half the sample to decompose. If I have a relationship that says log of A0 over 3, and this is 1 and this is 0.5 A0, then mathematically we worked this out so that we had a constant about 0.693 is equal to KT. And that would be the relationship you'd have for the half-life for a first order reaction. And that gives you some information that you can then use. The last problem that we did the other day said that the half-life was, I think this is the information, the half-life was 168 seconds, and you started with 1.6 molar and 15 minutes had elapsed, and you wanted to find out what you had. Was that what we did?
Yeah.
Okay.
Yeah.
All right, so the reason why you needed the information about the half-life here was so that you could find the specific rate constant, because the constant isn't given, and the relationships that you need to work with involve that constant. So if I want the constant, it would be 0.693 divided by the half-life. For those of you who already have this, you don't have to bother writing it again. 0.693 over 168 seconds, and that will give you the constant for this reaction. 0.693 divided by 168. And the reason why I'm doing it is because I want to do two things side by side in a moment. 4.125 times 10 to the negative 3. And we were able to then go ahead and plug this in. Log of 1.6 over I don't know is equal to 4.125 times 10 to the negative 3 times 15 minutes, 15 times 30 gives me 900 seconds over 2.3. This is per second. So the units cancel. So, remember what the answer was for this one?
Where did you get this?
Where did I get the what?
Where did you get this 0.693?
It's a constant.
Okay.
You get it by, the derivation involves taking the log of 1 over 0.5 is equal to KT over 2.3. So 2.3 has a number, multiply that, and then take that times the log of 0.5. Okay, so we got concentration of this 4.125 times 10 to the negative 3 times 900 divided by 2.3 gives you, for those of you who weren't here, and there were a number of you last time, I think you were hiding from me, but that's okay, I found you anyway. It's equal to 1.61. And now you have to take the anti-log because it's the log of something unknown. So on most of your calculators, it's just shift log. 1.6 over I don't know. Does it look right? 1.25 times 10 to the negative 3 times 100 divided by 3. Log of that, no, I know that's right, but my log didn't come out right. My box, I pushed the wrong button, 0.21. So 1.6 divided by 0.21. 1.6 divided by 0.21 gives you 7.6.
Would it be 41?
Then we try it again. Pushing the wrong button again. 1.61.
Isn't just,
I have to take the anti-log. 40.1. Thank you.
oh yeah, because I think last week she told us.
What's the matter?
Last week I had the 0.204, so did we not keep the analog last week? So when
Yeah, I just got this answer. So let me go back again. 4.125 times 10 to the negative 3
yeah,
times 900 divided by 2.3 gives me 1.6.
okay.
And now you have to take the anti-log of both sides. If this is 1.6, 10 to the 1.6 should be greater than 10. Should be almost somewhere between 10 and 100. So that's the only reason I like to use logs. And I have to take the anti-log of this, so on your calculator, it would be shift log. So I have 1.6 over A is 41.1. So now I push the right button.
You guys did that last week.
What did you do last week? Because we were rushing right at the very end.
You can
Oh, right, you
put
told us
on
the answer, that's why, never mind.
Okay.
Because we got 0.204 over M equals 1.6, and then.
That's a log instead of a log.
Okay,
But this is the anti-log here. You
Yeah.
need to take the anti-log of both
see,
sides.
that's why.
Okay. Don't ever try and get the whole lecture done in the last 30 seconds. So now it's 1.6 divided by 41.1 should be a concentration of 0.039 molar, which makes more sense. Okay, do we agree now? You guys are supposed to be my math checkers anyway when we do this. You were just in such a hurry to leave that you didn't even check my math, shame on you. I'm supposed to know the buttons, but shame on you for not checking my math. Okay? Now, I want to show you another way to do this, which may or may not make sense to you, but in the long run, it will work for a number of different kinds of problems. Okay? I'm going to make some assumptions, which can be dangerous sometimes. But after one half-life, what you have is equal to what portion of what you started with? After one half-life. What you have now is equal to what portion of what you started with? A half. A half of A0. Okay? After two half-lives, what you have would be a half of A0. Yes? Half of that. So it would be a quarter of what you started with. Does that make sense? So after three half-lives, you getting bored yet? After three half-lives, what you have would be a half of a half of a half of A0. I'm going to add a parentheses here. Do you see a pattern? How about after n half-lives? You would have a half. If it was three half-lives, it would be 1, 2, 3, but after n half-lives, it would be a half to the n times A0, or 0.5. What you have would be 0.5 to the n times A0. But this, remember, is the number of half-lives. This is the number of half-lives. Number of half-lives. And you can do that for any problem at all. For example, in this problem over here, I have 900 seconds, and my half-life was 168 seconds. How many half-lives have elapsed? Okay, I have 900 seconds divided by 168 seconds. Find out how many half-lives. 900 divided by 168 gives me 5.357 half-lives. So, what I can do is I can take 0.5 to the 5.357 times what I had initially, and I should get the same answer as I got here. Let's see. Today, with the math and the way the universe is working against us, I don't know. But anyway, I have 0.5 to the 5.357 times 1.6. You know how to do it on your boxes? 0.5, y to the x, or x to the y, 5.357 times 1.6, and I got 0.039. Cuts out a few steps. Sometimes it's easier. Whichever way you work it, it's fine with me. But you have to know how to do the problem. The reason why this works is because we're simply assuming that we know how half-lives work. Once we figured out how many half-lives have elapsed, 0.5 to that number times the initial. Over here, we use the half-life to find the specific rate constant and then plug into the problem. This will work all of the time without any difficulty. This, you just have to make sure of your math and make sure that the situation applies. And you should have no difficulty with it.
It has to be in seconds, correct?
Well, no, as long as the half-life is given to you and as long as the units match.
Okay.
Okay? So if this is If this is given to you in seconds, then this has to be seconds,
Oh, God.
all right? That's why I had to change this, it was 15 minutes, I had to change it to seconds in order to be able to work with it. If you had been given the half-life in terms of, say, 0.03 per minute, then you could have used it as it was. Okay, yes?
What was the original question about
The question would be, what's the concentration now of a substance after 900 seconds have elapsed,
Okay.
all right? But you didn't even have to find the specific rate constant for this one. You didn't need it as long as you had the half-life. In this version, you use the half-life to find the constant and then plug in. So, depends on what you're given, yes,
The 0.039 is
is the concentration, this is the molarity, because it's in brackets, so the concentration of this now is 0.039 molar.
So the question would be
What is the concentration
After
of this
65%?
reaction after 900 seconds have elapsed, if the half-life is 168 seconds? Okay, you want me to write it down? You need the question written? So these are variations, the same problem done two different ways, that's all. Right, so either one, as long as you're comfortable. I don't care how you solve it, as long as you have a correct way. If you memorize this, it will work for all iterations, all different kinds of versions of the problem for half-life in first order. One where you have to find a concentration, or one where you have to find a time. In this case, it would be a little bit more difficult if you had to find a time, but because you only would have a half-life, and then you'd have to go back into this formula to find a constant. Yes?
Does this question still involve 65%, or was that another question?
That was a different question.
Okay.
Different question. This was an iteration of the last problem that we did last Thursday. All right? Questions, problems? I'm making you confused, okay, but talk to me. It was given in a problem. It was 15 minutes times 60 seconds per minute to give you 900 seconds.
So what gave you 168?
I was given in the problem, if the half-life is 168 168 seconds. So you have to have something given to you. Go ahead. The 2.3 is a constant if you're dealing with logs. All right, if you're dealing with natural logs, then you don't have to worry about it. But if we're dealing with base 10 arithmetic, which is supposed to make it easier for me to see right away, but I'm still fogged at this one. So, it's just a constant that's used whenever you have base 10 arithmetic. All right?
Are there, or like, so like, this is an example of a question. Are there, in the slides, is it like the questions written out somewhere? Like, I know you said you could write it out, but is there like another example in the slides that we can?
Not of this variant, I don't think, because it's a cheap and easy way of getting around things. This is an example. This is how it's derived. You take a relationship and there we go. This is
Okay, that's fine. That's what I'm.
no, it's not. I didn't write it out, but the question basically is, by either method, find the concentration now for a reaction where the half-life is 168 seconds and 15 minutes have elapsed. Okay? But this is information that was given, it was 1.6 molar.
And it would say that A0 is 1.6 molar.
It would say that the initial concentration, let me write down problem. That's okay, I will write it, I will put it in English even.
It's just that's what I
English
think
is
that's
supposed to
part
be
of-
my native language.
That's part of the test is like reading a problem and understanding what it's
I
asking
understand.
for, because I just get confused.
All right, so in this problem is find the concentration of A if the half-life is 168 seconds and 15 minutes have elapsed. Or after 15 minutes have elapsed. if the initial concentration was 1.6 molar. I would probably say the initial concentration is 1.6 molar, and the half-life is 168 seconds. What is the concentration after 15 minutes of elapsed? But it would be something like that, and there is a couple of examples on that worksheet,
Yeah.
if you've looked at it.
Yeah.
And one has, the first order reaction has a half-life of this, if the initial concentration is this, what's the concentration of the reactant after 2 minutes have elapsed? That kind of thing, or after
How
some
long
amount of
will it
time. Okay?
Yeah.
Right, so you should be able to find an example, but the method
Oh, yeah,
will
it's
differ
understood.
depending on which method you choose, but the answer should be identical. And I just wanted to give you an easy way to go through it. All right, some people like this way. This is given to you here. Concentration of what you have now is 0.5 to the number of half-lives times A0.
And does this have anything to do with the order at all?
No, it's a first order reaction. This
Okay.
will only work for first
So
order.
it's only first order?
Yes.
So there's
Yes.
no question you can only answer for first order, so we don't have to
Yeah, I
worry
would
about
tell you that it's first order, you
Okay.
have to know that. The half-life relationships are different for other kinds of reactions, but because there's such a tremendously large number of first order reactions,
that. Okay.
most people spend most of their time concentrating on this. And if they have to do other reactions, other types of reactions, other orders, they usually go through the math graphically. It makes it a lot easier to deal with.
Okay.
All right, any
So-
other questions?
The inverse of log only works for first order, or are you talking about that?
No,
short?
what works for first order is the equation that we dealt with.
Okay,
And this works for first order reactions, because this is the half-life relationship for a first order reaction.
okay.
Okay? Questions? Anything else? Okay. You sure? Okay, you're in questioning mode, which is nice, that's a good thing. Because you should be able to puzzle these kinds of things out. If somebody told you that the initial concentration was 18, how much is there after 4 half-lives have elapsed? So half is gone, and then half of that, then half of that, then half of that. So you could work out the quantity. That could be a multiple choice question, that's not terribly difficult. This is a practical kind of an example. Iodine is sometimes used in rate studies because it decays very quickly. Its half-life is 8 days, and it's completely, to the point where it's not going to necessarily bother with too much. But after the first half-life, then you're down to half of the initial sample. So you had 16 the first time, then you'd be down to 8, then you'd be down to a half of that, then you'd be down to a half of that, then you'd be down to a half of that. Is there a point where you're gonna get to 0?
No.
It's diminishing, you're gonna get very close. Okay? All right. Second order. There are some relationships for second order, but you're not going to have to deal with them mathematically. I'm not going to ask you to do too much. The rate law for second order with time simply is that I can calculate it, but I need to have 1 over the final concentration minus 1 over the initial is equal to KT. That's just another variation on that. I just put them together on the same side of the equation. The half-life is given to you here, but for the most part, if we have second order, it's going to be something that we're dealing with in a lab situation. And I won't be asking you about its half-life, I won't be asking you about concentration and time. It's here for your interest and edification. It's not going to be here for a final, an exam question, unless you insist, and then I will put something on. Is anybody about to insist? Good, good, good for you. Okay, so this is a summary for you. And for the most part, concentrate on 0 order, first order, and the first part of this, make sure that you know what I would mean by a rate expression for a second order rate is equal to constant times the concentration of that squared, you know how to get a graph for a second order reaction. You won't have to worry about the half-life or concentration with time, as you will for these. Okay? Problems? Piece of cake. See, you're almost done kinetics. The only thing we didn't really consider was the effect of temperature. And that's what you're supposed to be doing in lab this week. God help us all. They're redoing the solution, so hopefully Thursday's lab will actually work. We had some fun today in lab, and that's all I'm going to say about today. Okay, but you were very nice. You didn't throw things. Anyway, this graph looks like something you saw at the very beginning when I was talking about factors that affect the rate of a reaction. I gave you this curve and flashed it up on the board and talked about the fact that generally if you warm things up, you're going to tend to increase the rate of the reaction because the particles are colliding faster. And what happens is if you warm them up, you wind up having a greater fraction of the molecules that are actually going to be able to collide with each other because the collisions are occurring faster and faster and faster. So it's much more likely that there'll be an effective collision. It's much more likely that they'll collide with the correct geometry. So the number of effective collisions increases as the temperature increases. You have sort of kind of the same general shape curve, but at the lower temperature you have a smaller fraction of the molecules actually going to react than you would at a higher temperature. So what your problem is how do you relate this fraction, this number of molecules that are actually going to react to the temperature? From the statistical theory of gases, published by Arrhenius, one of the things that he did was to actually figure out what that area under the curve would look like. And for this, the relationship is that this area of the curve, let's hope this works, this area would be given by e to the minus some energy over r times t. That's not showing up, that's a t, come on, t. So this is the area under the curve. So we can relate this information now to say that the number of particles that are reacting, well, the number of particles that are reacting is actually similar to the rate, but we can extend that a little bit more and say that according to Arrhenius's idea, that if I want to say that it's proportional to the rate, it's really more likely proportional to the constant because we're running this at different temperatures and the constant is going to be dependent on the temperature. I would say that that's equal to some factor depending on that, remember, because it's got to be proportional to, so we need a constant of proportionality, e to the minus EA over RT. Well, some of this is garbage. You may not be able to work with it all. So one way of cleaning that up a little bit is to simply take the log of each side. If you take the log of each side, then you have the log of the constant is equal to minus EA over RT, which is good because now it's actually in the form of an equation of a straight line, where this would be y equal to mx plus b, where this natural log of a would be the y-intercept, the slope would be minus EA over r, and this x would be the 1 over t. So this is 1 over the temperature in Kelvin, and m would be minus energy over r. So all of this is given to you here. R is a constant. We love it. It's the ideal gas constant, but remember which one you can use. If this is one that's going to be dealing with energy, the R is going to be 8.31. 1 over the temperature's in Kelvin, and we're still trying to figure out what the heck that thing is. What would that have to do with? Well, if we're talking about the number of particles that are actively going to be able to collide, you're really talking about the frequency, how many particles are actually hitting in a unit of time. And this is then going to be considered something called the frequency factor, which doesn't help you a lot, except if you want to just plot the log of the specific rate constant versus 1 over t, you would wind up with a lovely little slope. If I plot the log of the specific rate constant versus 1 over the temperature, I should be able to get a value that is going to be able to give me the energy of activation. Yes,
I'm developing wrinkles on my head, just.
go ahead, talk to me.
confused.
Go ahead.
What did you just say?
In English, what we're going to do,
I see the slope of the line.
okay,
That's all I see, and I was,
this is, the slope would be minus EA over R and 1 over T. So I'm just going to separate this out. So
yeah,
this would be 1 over T, so that would be your X value, okay? So what I'm saying is that if I had a way of measuring the specific rate constant versus the temperature, I'd be able to plot a line. If the temperature changes, I'm going to be able to get a line. And if I can get a line, then I'll be able to get the slope.
Yeah.
And because this is known, R is a constant, then I'd be able to figure out what the energy of activation was. And you know what energy of activation is. It's that extra energy hump that you have to overcome in order to make the products come about.
okay.
All right, so it's a useful concept. Finding the energy of activation is really, really useful. And it's the kind of thing that you want to know because most of the reactions are going to have an energy of activation that you actually would have to either overcome. If you were in a lab and you know that this reaction happens, but you haven't given it enough of an energy of activation to get it started, you'll be sitting there freaking forever trying to get the reaction to go. If you know that you have to supply extra energy, then eventually you're going to be able to figure out, well, I might have to crank up the reaction vessel to 400 degrees in order to be able to give it enough energy to go. Question?
Yeah, I was trying to take this model and apply it to the lab. And, even though there was a reaction, it wasn't what we were looking for,
Right.
but if you take the temperature, for example, in Kelvin, you're talking, and you're saying it's what's held constant? For
No.
that particular
For your
reaction,
trial,
or,
you were supposed to do it at 20 degrees, then at 40 degrees, and then at
Right.
50 degrees. So you would have 1 over
1 over
the
20, 1 over
293.
30,
Yeah,
whatever.
well, in Kelvin.
In Kelvin, sure.
Okay.
One
So
over
what should
200.
happen is that when you take the natural log of the constant for that reaction, you should get some data points. Now, because
Where's your constant for the reaction coming from?
in the reaction that you did in lab,
Yeah.
because everything was all kept, the reaction was done the exact same way, then they made a workaround. They did something called a relative rate. And what you did was instead of the,
Repeat that.
go ahead. Because all of the concentrations were the same, and
Yeah.
because you actually had 2 reactions going at the same time, you were supposed to have a reaction with persulfate
Mhm.
and then with thiosulfate rather.
Yeah,
Because that happened, or was supposed to happen, you weren't able to calculate a constant for a particular reaction. You were using a workaround. You were using something called a relative rate.
okay.
And your
So that-
relative
so
rate-
Relative rate is our constant.
Yeah, your
Okay.
relative rate is going to be the log of 1 over the change in time. All right, so you were supposed to graph time, 1 over time versus
And
1 over
relative rate
temperature.
is used in the absence
Relative,
of.
relative rate is used in the absence of, I couldn't figure out any other way to do it, honest to God.
That's fine, I just,
So you're gonna take something that you can measure about that substance. Now, it was supposed to be a color change. And the color change was supposed to be measured, it was supposed to take a measurable amount of time.
mhm.
All right, so sometimes what they'll do when they have a reaction where there's actually 2 or 3 reactions involved in order to get it, what they'll do is they'll just take a number, say like 1,000 divided by time and get a relative rate.
1 or 2 reactions before you end up with your final
Yes.
product.
Because in this
Okay.
reaction, you were supposed to get one thing, which was then supposed to react with something else.
Sure, and
So-
then produce a final
And then
solution.
get the final blue color in your case.
Okay,
But because it wasn't one specific thing, you couldn't go through the process of finding the actual specific rate constant for that reaction. You would have to find the actual specific rate constant. It would have actually been longer if you had to find the actual specific rate constant, because you would have had to know the order with respect to each of the reactants, you would have had to do all of the rest of the stuff. So sometimes this workaround is like, hey, cool, makes it go fast, because you're getting a relative rate based on something that you've timed. And since all the reactions are the same, you're just saying, well, comparing this one to that one, the only thing that's changing here is the amount of time. All right, so we're just going to say, well, let's pretend that that's going to be a factor that's going to be related to the rate of the reaction. And the things that are related to the rate of the reaction are the specific rate constant, or a relative rate that we've made up. All right, so it's just something related to the rate of the reaction. So something that we can judge. Usually it's the natural log of the specific rate constant. I've seen them actually do rates here when they had difficulty finding a constant. Something that you can judge that will tell how fast something is going. And as long as all of the trials that you've done are at the same exact concentrations, done under the same exact conditions, then the only thing that should change about the reaction, if you change the temperature, you should change the time, the amount of time that this is going to take. Okay? So it was a workaround, and it may or may not come to fruition in terms of Thursday's lab. The data that I gave you is from a real lab that they did last semester, and they did see that the warmer it was, the faster the reaction took place.
sure.
And that's what you should expect in general, that as you increase the temperature, because you're increasing the number of collisions, the reaction should progress much more quickly. And hopefully you'll be able to see that from this week's lab. I don't know. If you can't, then I'll make up some data that's based on last time. But it does usually work. Now, the only problem is, what the heck are you gonna do with this stupid equation? You're stuck with it now. I mean, it's lovely that you have this Arrhenius equation. It's wonderful that you have an equation that looks like this. Isn't that nice? That's a wonderful equation. And with this equation, you can write it in any form, any variation you want. That's a variation on it. That will be nice. But a lot of times, you need more information about a reaction, or you care about more kinds of things than just this. You're not going to operate from one data point, or you're not necessarily going to go into the lab all of the time and be able to calculate a slope. If you're stuck in a classroom and somebody says, well, how much faster does this reaction happen if you increase the temperature by 10 degrees? You go, well, let me run to my lab and figure it out. No, you don't have to, because there are some workarounds. What you can do is you can consider the same exact reaction done at different temperatures. The constant would be a little different, temperature would be different, but the energy of activation would be the same, and the frequency factor would be the same. So what I did, and some of you aren't going to like it, is to give you a way of getting to an equation that you'll actually be able to use for calculating the effect of temperature on a reaction rate. And what, if you take a look at this, this is the derivation. And I handed it to you because no one can ever see it when I throw it on the board. Okay? So just take a look at this. This is the general information. Yeah, if you guys didn't get stuff in the front of the front table, then come get stuff. Okay? So I want to just talk it through with you guys. It's not anything where you're going to have to memorize a derivation, all right? You're going to have to bottom line it. but I wanted to show you where it came from, because nobody seems to trust me anymore. You know, you only don't have to trust me when I'm doing simple arithmetic. The rest of the stuff I can actually do. All right, now, what we're gonna do is consider this, consider a reaction that's done at different temperatures. And we wanna see how we're going to actually affect the specific rate constant, because the constant does change with temperature. So, we know that if we take the Arrhenius equation, which can be written as the ln of K is equal to minus E sub A over R times 1 over T plus ln of A, or if I did it in base 10 arithmetic, fine, not a problem, log of K minus E sub A over 2.3R times 1 over T plus the ln of A. Same thing. So what I'm going to do is at two different temperatures. So here's my first one. Here's my first one. If I do a second one, then I have log of K2 minus E sub A over 2.3R. This stuff should stay the same. 1 over T2 plus the log of A. So what you can do is just subtract those two equations from each other and get rid of some of the garbage. We need a way to take out some garbage. You don't know that frequency factor off the top of your head. You don't care about it most of the time. You know, maybe if you're graphing you care about it, or maybe in a problem that I'll give you in a few minutes you care about it, because I want to show you what the size of the number is going to be. But the easiest way to do this is just to subtract these two equations from each other. If you subtract them, two different temperatures, then what you're left with, you're going to wind up getting rid of this log of A. This will be a factor in common to both of them. And then you're going to have log of this, 1 over T1, 1 over T2. So you're going to wind up with an equation that may look a little bit familiar to you. And you wind up with log of the K2 minus log of the K1 would be equal to minus E sub A over 2.3 times 1 over T1 minus 1 over T2 minus 1 over T1. Does that make sense? So now what you need to do is to put it together in a format that is a little bit easier to work with. And one of the things that you should probably do is to get a common denominator for this nonsense. What's a common denominator for 1 over T2 and 1 over T1? Common denominator would be T2 times T1, and then multiply through, and then you can get the factor that you get. You can also go through and get rid of some of the negative signs, but if you get rid of some of the negative signs, then what you're going to wind up with is switching a few things around, and some of you might not be comfortable with that. Question?
Is your R 1?
Hmm?
Is the R a 1?
No. I'm sorry, it should be there too. Okay, but that's a common factor to both of them. Thank you. All right, so when you put it together in a format that's easier to work with so that you can have a fast, down and dirty way to work with it, you wind up with something that looks like an equation you've already seen. 2.3R times T2 minus T1 over T2 times T1. That look like anything you know? That's how the Clausius-Clapeyron equation is actually derived also. But now we're talking about an energy of activation, not a deliquorization. And we have ways now that we can work with specific rate constants at different temperatures. We can also, if we know the specific rate constant at different temperatures, solve for an energy of activation. So it is a useful formula, if a little bit tedious to see how it was derived. But you can go through and check out my math and make sure that you multiply through to clear out the negative numbers. Okay? So now we have bottom line formula. So now we need to do problems. And at this point, you guys are gonna have to know the formula. You're gonna have to be able to work with it. And if you have if you wanna use natural logs, the only thing that's different would be natural log, and then you would leave out the 2.3. Yes?
Why does it say 2.1 on the bottom right of the board? Is that
No, that was just if you were trying to find a common denominator for that.
okay.
Okay, I'm erasing all of the extra garbage. So here's our formula. Log of K2 over K1 is equal to energy of activation over 2.3 R times T2 minus T1 over T2 times T1. And I need to give you some problems. There's problems on your sheet. Let's see if I have something to answer for you. Huh?
On the board.
Do the one that's on the board?
Yeah.
All right. Got it done for you, but okay. I'll got it. Yeah, we'll do for the next one. Here's the answer. Okay. But we'll do it.
Yeah.
Okay. All right, so you want to find the energy of activation for hydrolysis of sucrose to fructose and glucose. That's just words. All right, you don't care. What you care is they give you the specific rate constant at one temperature. And remember, the temperatures are going to have to be in Kelvin. Anytime a temperature is going to wind up in a denominator, you have to make sure that the temperature is not going to be 0. So you're going to use Kelvin. So we have K1, we can say, is 2.1 times 10 to the negative 11 when the temperature is 300 Kelvin. And K2 is 8.5 times 10 to the negative 11. And this is a first order reaction, they're both per second, so it's a first order reaction. When the temperature now is going to be at 37, so 310 Kelvin. And I want to find out the energy of activation.
And
So
both in seconds.
they're both per second. Okay, so that's something that should be written in, and it would be written in a, I just used the wrong eraser. It would be written in an actual problem per second. At least they're straight. All right, now, it's so hard that now you just have to plug it in. You got the formula, plug in. Yes, ma'am.
Are we always know what R is?
R will always be given to you, but I usually put both values. You have to remember that if there's any kind of a relationship where you're dealing with energy, then the R value you need is the 8.31, not the one you memorized for gas law.
0.0821?
Yes. All right, so you didn't need it anyway. So, plug them in. Log of K2, 8.5 times 10 to the negative 11, divided by 2.1 times 10 to the negative 11 is equal to, I don't know, over 2.3 times 8.31, this is joules per mole Kelvin, times 310 minus 300 over 310 times 300. Okay, I know I make you guys crazy, but is there anything about what I've done here that's making you crazy? All right, we've got a formula. Derivation didn't matter, we've got formula. If you have formula and you have numbers, you stick numbers in formula. That's all you gotta do, okay? You got two numbers on the log side, so divide and take the log. You have 8.5 times 10 to the negative 11 divided by 2.1 times 10 to the negative 11 to give you 4.05 about, and you need to take the log of that.
I got a different answer than that.
Huh?
Oh, never mind.
What? Question?
You said a number out loud, but then wrote a different number down.
Because I had to take them off.
Okay.
Did you
Oh,
take?
you just, okay, you didn't do it all together, okay. You wrote down the number I have, but when you said 4.5 out loud, I was like, that's not what I
Yeah,
got.
and then I took them off. Okay. And now on this side, you have energy of activation times stuff. So I have 310 minus 300 gives you 10, divided by 2.3, divided by 8.31, divided by 310, divided by 300. If it's in the denominator, push divided by. And you have 5.62 times 10 to the negative 6. Do we agree?
Not yet.
Okay.
So I have a question.
Yes.
Will you always give us the value of R?
I will always give it to you, you just have to know which one you're using. Like in the last test, you had both R values. You just have to know that if it's energy, it's always 8.31.
I didn't, oh,
What, we have something different?
yeah.
What you get? All right, push along with Clapper.
Okay.
You got
Oh, wait,
10.
wait,
Subtract here gives you 10, right?
okay.
Then push, divided by 2.3, divided by 8.31, divided by 310, divided by 300. Because if it's in the denominator, you can keep pushing divided by,
Okay.
all right?
It doesn't matter that it's a negative 300?
No, it's not, this is multiplying.
Oh.
You
sorry.
subtract it here to get your 10,
That's right, T1, T2, pardon me, I just.
okay? Keep me honest. And you should get a big number in your answer, because the energy of activation should be certain number of kilojoules. So right now, my energy of activation would be 0.607 divided by 5.625, actually, times 10 to the negative 6. So we're going to get a big number. Should let's just times 0.607. Somebody's allergic to energy of activation. Okay. So what did you get? You're not pushing along with
Oh,
Clapper
I
here.
am pushing along with the top.
Okay. What did you get?
You gotta sneeze, you can't.
I know, but not just Mercedes, everybody should be punching along here.
1.07 times 10 to the negative 7.
I gave up a long time ago.
I got 1.08 times 10.
Times something to the fifth. If you get somewhere in the neighborhood of 1.0 something, I got 8, times 10 to the negative 1, 2, 3, 4, 5. 10 to the fifth power, rather, would be my energy of activation. Yes?
A lot of us have a negative
Negative 7? With what? With this? With this number?
No, the answer, but it was 1.08.
0.607 divided by 5.62 times 10 to the negative 6 gives me big number. Yes?
I got 104 times 10 to the
Fifth? Okay. Depends on how many decimal places you carry it out to. If you just
Oh, I
kept it
tried the
running,
equation.
yeah, if you kept it running, then it's supposed to be that. All right? All right. So we're having dueling calculators right now. Questions? Where did we get lost, guys? Because you got to be able to do this on your boxes.
About an hour ago.
What last part?
I'm probably doing it.
Just divide 0.607 divided by 1.
I'm probably
1.08 times 5.607 divided by 5.62 times 10 to the negative 4. That's fine. Yeah, no, 6, I'm sorry. 6, I can't. You are good in that far away. Okay? So, think about it. It's going to be positive, and it should be, if this is 0.6, it should be 50 to
my
the
asthma
fifth
inhaler.
power by the time you're done.
fine.
Right? Here. No, positive.
No, I got it.
Right.
There's never been a problem.
Okay. Yeah, I know. Yes, I know, I'm sorry.
That's fine.
Yeah, okay. All right, questions? Your graphing calculators don't like you, but, you know, that's why I have my Chico Casio equals. Let's say I'll staples, yes.
I can put it in a log and then the 8.5 times 10.
Divide and then take the log.
Oh, so I divide it first. and then-
Divide and then take the log. Yeah, proceed.
So, when you're doing your calculator for the final answer, it takes a big number, and we get points off if we don't put it into the 10 to 5.
As long as you get something that's a big number, yeah,
We don't
it's
have to
fine.
put it in standard notation.
No, I don't care. Sometimes people do it this way so that they can quickly put it in kilojoules per mole, because that's how it would normally be found in the references. It would normally be found in terms of kilojoules per mole, and sometimes it's easier to see, you just change the decimal 3 places.
I was saying, I how.
Fine, no, at this point, if it's a test question, if you know how to do the thing, that's fine. All right,
Thank you.
any other minutia? Questions, problems, it's boxes and significant figures and how far do I carry it? But the question I wanna ask you is, can you put the things into there and get an answer? That's all I care about. If you know how to solve it, all right? This is how to. This is not, I differ from you in the 4th decimal place. This is, can I actually use the right equation and get an answer? All right, so,
Quick question.
yes.
What if we were asked to solve for K1? How in the world do I like?
Piece of cake. We're gonna do that now.
Oh, anti-log, right?
Yep,
Okay, never mind.
yep.
Wait,
Alright.
you could explain it.
No, we're gonna do it. We're gonna do it now. This is the first question. All right, second question. Second question. Okay? Find the constant, and we'll make it at 290 Kelvin.
Ugh.
Find the constant at 290 Kelvin. Can you do that? Yes. Go ahead.
Which K would that be, the both Ks?
I want to find a new specific rate constant. This is at lower k, at 290 degrees Kelvin. All right? So what your option is to pick either of the two that you already know. All right? Because you know it at 300 and you know it at 310. But now you want to find out what the constant is at the 290. But being a brilliant chemist, you know the energy of activation at this point. And because you know the energy of activation, you can go ahead and solve it. So your problem number 2, this is number 1,
Okay, so it'd be part 2 of that.
and number 2, continuing the same problem, you can choose one of the previous sets of data and now use your other temperature. So whichever one you want to find and make this your K1, that's fine with me. So I have log of K2 over K1 is equal to energy of activation over 2.3R. I know I'm obsessive compulsive, I'm writing the whole equation again, but that's fine.
Yeah.
Over T2 times T1. The more times you write it, the easier it is to do. So, I'm going to say, let me do the 300 one. Log of 2.1 times 10 to the negative 11 over I don't know is equal to 1.08 times 10 to the 5th over 2.3 times 8.31 for whatever, times my K2 was 300, my K1 is 290, times 300 times 290. Now you've got all the numbers on one side of the equation. So you do that side of the equation, get a value, and then you'll take an anti-log, just like you said. All right? So this works out to be 10. 1.08 times 10 to the 5th times 10 divided by all the garbage in the denominator. 1.08 exponent to the 5th times 10 divided by 2.3 divided by, I'm saying it out loud so you can punch along with Clapper, divided by 300 divided by 290 gives me, on this side of the equation, 0.65 about. And then on this side of the equation, I still have log of 2.1 times 10 to the negative 11 over I don't know. Did we get 0.65? Or something like that? Sort of, kind of? You just gotta stop talking to me. It's not time to stop talking to me yet. You got 6.2. I got 0.649499 something. Whatever, it's a number, it's a thing. We got around 0.6 something? Or 0.649, 0.65.
Yeah,
Okay.
6.49.
We sort of kind of agree, sort of kind of. All right, so we're sort of kind of going to agree on that. Now, how do you find out the constant? You have to take the antilog. So you take the antilog of each side. Antilog of this side, and you're going to take the antilog of this side. That means you have to find the number whose log is 0.65. If this is 0.65, then you know that on this side of the equation, the number is going to be less than 10. All right, so you got a working hypothesis here. On this side, if I take and find the number whose log is the log of that, then I cancel out the word log. And I wind up, I'm going to just put it over here, guys. Oh. I wind up with 2.1 times 10 to the negative 11 over k is equal to, and I take the shift log of this, and I wind up with 4.46. Okay? And all I'm doing is taking the shift log of 0.65, 0.65 shift log. Or 10 to the 0.65 power. All right, that's what you mean. That's what it means. If you have a y to the x, you can push it to 10, y to the x, 0.65 if you want. Same difference. All right, so now how do we get k? Yeah, just divide that thing. Okay, so I have times 2.1 exponent, change sign to the 11. Now, should it be greater or less than the initial one? What do you
Less.
think? Should be less because the temperature is lower. And what I got, and you can all debate me, but what I got is 4.71 about times 10 to the negative 12. And it should be smaller. Okay? As you increase the temperature, you should be increasing the rate and therefore increasing the constant. All right? You okay on that? You look like you really want to throw those
But is that the
calculators.
opposite of what we did this time, and then we increased the temperature?
In this case, we went down to 290.
So when you decrease the temperature, the
The
constant
constant
gets
should get smaller.
smaller. Okay,
I said when you increase the temperature, the
so
constant
the
gets
opposite of
bigger.
what we did in this problem.
Yes,
Because had we increased it, our constant would have gotten larger.
which is what happened in the first one. We increased the temperature, notice the constant was bigger for the K2 versus the K1 in the first try. Yes.
And, since, for this question, we pay at 290, like, we decided that was K1.
We decided it's either one, as long as you use the data set together.
So if that's the case, like, I noticed we put,
You could have called it K2, but then the temperatures would have been different.
okay, that's what I'm saying, not just the temperature. So
Yes.
if you make it K2, that you have to have that.
Doesn't matter.
Okay, just making sure the numbers have to.
Yeah, as long as the subscripts that you've chosen, as long as if you say that that's one, then the temperature has to be that temperature one.
Okay,
All right?
alright, yeah.
All right, anything else that's making you crazy about that? You sure? Okay. There is an example of this. That's how we got the 1.08 times something like that, times 10 to the 5th. And there are some other things that you could do, but those are the two most frequently done types of problems. I could ask you to solve for a frequency factor, but I don't have time today. The frequency factors, you would actually have to plug into the Arrhenius equation and solve for the ln of A if you wanted, but I don't know at this point you actually believe me on anything anymore, but you get incredibly large numbers, somewhere in the neighborhood of 10 to the 25th, 10 to the 30th, very large numbers, because we're talking about the number of collisions per unit of time that are going to be likely to be effective, and they're going to be relatively large. All right, we have one last thing that we have to talk about. And I'm not going to necessarily do everything I probably should for reaction mechanisms, but you know what a mechanism is. A mechanism is a series of steps by which you actually go from reactor to products. And sometimes there's maybe 1-2 steps that are important. Sometimes there could be 8 to 10 steps that are going to be involved in your reaction. But the actual sequence is the reaction mechanism. It may involve some intermediates. Very frequently it'll involve an intermediate. When you made your aspirin, first thing the phosphoric acid had to decompose, and then the hydrogen had to go and sit on the acetic anhydride. And then that had to break up. And then you wound up with a radical that was about to react, but that wasn't the final product. Something else had to happen. So that reaction produced something that was intermediate that was then used up in another step. So that frequently happens. And if you know, in general, if you have a reaction where you have to go from A plus B gives you E, sometimes it would go A plus B gives you C, and then C plus 2B gives you E. Whatever. Which is the reaction intermediate here? Okay, just get rid of that one. The C's gone, and if I add these up, I have 2 steps. So I have A plus 2B goes to A. This is a reaction intermediate that formed, but then it was used up. So it doesn't appear in the overall equation. One other thing that you have to worry about sometimes is that if you're dealing with kinetics, usually one of those steps is longer than the others. One of those steps slows the process. The part where you actually needed these things to happen in order to get to the product. And usually you can figure out which things are important if you look at the rate law, because the rate as it's determined experimentally will give you an idea of how important each thing is to a particular reaction. And usually those things that are important to the overall reaction will be the species that appear in your rate equation. So very often there'll be a really slow step. That's what's called your rate determining step. And then you'll have a whole bunch of things maybe that happen really fast. So your reaction takes place, if this is your slow step, this is sometimes what's called your rate determining step. And this is usually going to be proportional to your rate equation. If I had this as my slow step, and then this was really, really fast, what do you think the rate expression would be for this reaction? You might be able to guess it from this. What do you think the rate expression would be from this? If 1A combined with 1B and made something, but it was really, really slow, and then other stuff happened and it was really, really fast, what do you think the rate expression might be for something like this? Rate's going to depend on some constant, but I need one of these and I need one of those. So very often, the slow step can be determined right from the rate equation. I have one of those and one of those. You don't know that yet.
It's still
But that's okay.
first order.
Because I have one of these and one of these. Because each one of these steps of a reaction mechanism is going to be what's considered to be a, quote, elementary reaction. An elementary reaction is a specific step of a rate mechanism, of a mechanism rather, for a reaction. And when you're dealing with these things, you have to consider a couple of things. If a reaction is unimolecular, that means that one molecule has to do something, just one. So if it's unimolecular, it depends on that one thing rearranging. So the rate is going to be equal to that one thing doing something. It's going to be a constant times that one thing doing something. It's going to be a first order reaction. If it's bimolecular, then two things have to actually collide at an instant in time. So in this case, the rate would be equal to a constant times one of these times one of these. They have to hit each other. So it would be a constant times a to the second power. When you talk about molecularity, you're talking about how many molecules are actually involved in a particular step, how many actually have to collide in an instant in time. If you have termolecular, it gets really hard because three things have to collide simultaneously. You have to hit the lottery, and it has to be on a day that starts with a T and a month ending in R. All three things have to happen simultaneously. Likely to happen? It could happen, but it gets less likely. So if you have a termolecular reaction, the simple step for that would look like K is K times the A to the third power. So what we're doing is considering molecularity of a particular step, of a particular reaction. Each individual step has its own molecularity, okay? And the molecularity for each particular step corresponds to what that rate expression would look like for that particular step only, okay? All right. Now what we have when we deal with these things is something called an elementary reaction. What I have here is an elementary reaction. A plus B goes to C is an elementary reaction. C plus B goes to E is an elementary reaction. Each one of these things can have its own rate. We just defined that. This one would occur quickly, very quickly, but it still has a rate in general. So what would you say about the overall rate for this reaction? All right, because this is a question I always give, and somebody always gets it wrong. So let's listen to the question. The overall rate is equal to the slowest step. The overall rate is faster than the slowest step. The overall rate for the reaction is slower than the slowest step.
Impossible. Overall rate of reaction is slower than the slowest?
Yeah.
Slower than the slowest. The slowest happens to be the slower than the slowest.
All right, in English maybe, but a couple things have to happen for you. Couple things have to happen for you to get out the building. Okay? First thing, you have to get out the door. Okay? And if everybody's trying to hit the door at once, that's going to be pretty slow because you're all going to be playing Three Stooges, you know, bumping into each other at the door. After that, you have to get downstairs. The overall reaction involves getting out the door and getting downstairs. The slowest part is getting out the door.
Gotcha. So the
overall rate for the reaction is going to be slower. It's going to take longer.
it's your bottleneck.
Yes,
Got it.
it's going to take longer than just the bottleneck because you also have to then get downstairs. So this one's slow. This one's really fast, but it does take some time. So the overall rate of the reaction is going to depend on both of them. this is gonna contribute most of the time, but this is gonna contribute a little bit of time. So it's gonna be, take longer than just this first thing. So when I said slower than the slowest step, that's what I meant. It should say that it should be longer than just the first step. Okay, does that make sense? In English, sort of, kind of?
So you're adding the two.
Yeah, you're adding the two
together.
reactions together, yes. Okay, because each of the steps of the mechanism has to be accounted for. And that's why sometimes you don't get whole order values. Sometimes this rate determining step occurs later in the mechanism. So sometimes you can get fractional orders, sometimes you get things that are very peculiar looking in real life for the order with respect to a particular reaction. Yeah.
Sounds like you're saying that the rate of the overall reaction is slower than the rate of the slowest step in the reaction.
The overall, because this overall reaction takes longer because there are several steps to the mechanism. Okay? The first step, if this step took 20 minutes, this took 20 minutes, and this took 5 seconds. The rate equation would say that rate is equal to something that would give me something that relates to the 20 minutes. But the overall reaction takes 20 minutes and 5 seconds.
So the overall rate isn't.
So, yeah, I know. It's the semantics of it. It's how they describe it. Let me make it crazier. I'm not going to clear it up. I'm going to make it crazier. All right, I'm going to give you a hypothetical reaction. And let me find you one. I'm going to give you a hypothetical reaction, and then I want you to propose a mechanism for me. Okay? And from this thing, we're going to see if we can figure out a little bit about mechanisms and about the rates for reactions. So, I'm going to give you a bunch of hypothetical steps, hypothetical elementary reactions. An elementary reaction is a single step of a reaction mechanism. So I'm going to give you a couple of possible steps for a reaction mechanism. And I'm going to give you an overall reaction. And I want you to combine them in such a way that you'll get the final reaction and figure out the likely sequence. Okay, so we'll do an easy one first. We'll do the overall equation. You're going to get 2 pieces of data. The overall equation is 2L plus M gives you N. And the rate step for this, the rate for this reaction, the rate expression is constant is equal to L times M. So therefore, it should be first order with respect to L and first order with respect to M. And you've got a bunch of steps. So here are your possible steps. And you're going to have to figure out the mechanism for this reaction. So your first step, L plus O goes to N, and it's fast. Second possible step, 2L plus M goes to O, and it's slow. Next possible, L plus 2M goes to N, and it's fast. Next possible, L plus M goes to O, slow. And next one is L plus M goes to N, fast. Okay. Now, breathe. Okay? Each one of these is a possible step. Somebody did something related to these chemicals sometime in their life, and they figured out a relative speed for these reactions, a relative rate. But we have 2 pieces of data. One of them is the rate law. According to this, the slowest step should involve which chemicals and in what proportion of an elementary reaction. It involves L and it involves M, both first order. Okay? So my first step should be slow, and it should involve L and M. Do I have an L and M as a slow step?
Yes.
Yeah. Okay, L plus M goes to O, and that's a slow step. But O isn't in the final equation. Look at my equation. And I have one other thing that's missing in that equation. I need to have another L. So what I have to do, since this is the slow one, I need something that's got to be fast, because it doesn't affect the overall, the major, bottleneck part of the reaction. All right, so I need a fast reaction. And it has to get rid of O, because O is a reaction intermediate, right? It doesn't appear anything in any of this data that I gave you. So I have to take out the garbage. So evidently O is garbage. And what else do I need? I need another L. And I need a product. Do I have something that has an O and an L and makes an N? Yeah. And that's a fast step. Yay! So my reaction mechanism would be D and then A gives me my final product. That's my mechanism. All of those were possible steps, but this matches with the data that I have. I have a slow step that matches the rate expression, and I know you want to go. And then I have a fast step that gets rid of this reaction intermediate, that's gone, and adds the other L that I need in this equation, and gives me an N. All right? If you need to do another one of those when we meet next time, thank you for being patient with me, by the way. I owe you 2.5 minutes of your life.
Which I'll never get back.
Yeah, well, actually, you already got it back. I mean, I gave you like an hour, actually 2 hours for the last test.
I just want to make sure I wasn't.
How much of this do you actually understand? I'm just like scratching my head, writing down scribble scrabble.
I know the last part.